Today it's a pleasure to have our own Sreenivasan. Srini, his hours in some sort of sense, he's sort of delocalized over NYU completely. He's a member of the physics department, the mechanical engineering department, the math department. He's head of the Canyon School in Brooklyn, and the engineering school he has. He's also been all over the world. He's been a professor at Portland, Yale, and he's also been dean, head of departments at all of those places. Here, and vice
I don't know. Yeah, you can think of anything you like. Yes, yes, yes.
He got his degree at Bangalore University in his bachelor's degree, and then his PhD from the Indian Institute of Science in Bangalore. Is that what it is? He's a member of the Academy of Science on at least 4 continents I know of. One of them being the National Academy and National Academy of Science and the National Academy of Engineering in the U.S. He's got lots of prizes. There's like 4 of them. There's the Adela Port Memorial Medal of the APS. There's the National Order of Scientific Merit from Brazil. I could go on. The one thing I like best is a fellow of the Lions Club. Okay, and I can't tell you what we're going to talk about today. That's something to do with Brooklyn. High temperature, quantum, classical, all over the place. Srini?
Thank you, Paul. For one of our own, it was a very long introduction. Thank you for that. Paul is right. He didn't ask me what the title of my talk would be. I didn't give him any. So that's what it will be, what I do in my spare time, so to speak. But I won't keep you in suspense for too long. Maybe I should tell you a little bit about what I've been doing in the last few years, mostly because many of the people in the department have changed since the time I came here, and I haven't really kept track of people, and they haven't kept track of me. So it might be a good idea for you to know what the heck I've been doing the last few years. And then I will say a little bit more about one specific aspect. So one of the things I've been interested in is in thermal convection. This is the kind of fluid motion that develops when you have a temperature gradient against gravity. And we have designed now a new experiment using liquid nitrogen, and it's on a rotating table, but we don't have any results yet. But since I pushed the Rayleigh number, or the control parameter in the problem, to very high levels in 2001 or so, 10 to the power 17 to be more accurate, and nobody has been able to go past that even today, including us, I was naturally inclined to look at higher Rayleigh number phenomena. So I was interested in how convection happens in the sun. And then what do you know about the sun except through modeling? But you can infer what's inside the sun by doing helioseismic measurements. And so one of the important results we got was that the convective velocities, as you measure by helioseismology, measure within quotation marks because there are many intermediate steps, was about 1 to 2 orders of magnitude smaller than what people generally had thought. And that actually puts the whole thing in a different frame of reference. And so that's still being sorted out. And of course, computer simulations also. But I gave this talk on thermal convection very recently at the Simons Institute, and I didn't feel like I could reproduce that for you here. So I will skip that. Likewise, I've been working on turbulent mixing, mostly through numerical simulations. The size of the box, this is done with my collaborators. I don't really know how to program these huge computers these days. These are simulations of mixing on boxes which are almost, this is the maximum that is possible with the machines available, at least on the right side of the fence. 16,384 cube, which is a massive calculation. I remember the time when simulations were made on 32 cube boxes, so in my own lifetime it has changed enormously. I gave a talk on this in Courant Institute not that long ago, and again I think I should not really reproduce myself. There may be better ways of doing it. Quantum turbulence, the experiments are sort of winding down, but more things are happening with simulations. But I gave the colloquium on quantum turbulence here. You will not remember. So what is left? There are a few things I think about all the time, and that's the topic for my discussion today, which is a few basic concepts about turbulence. And what I want to talk about are here. How do turbulent flows dissipate energy? Every flow, except superfluids, dissipates energy. That is, you have to feed in energy for maintaining them. But how does it really happen to dissipate energy? You may think this is a very trivial question, but it's not, as I will show. And there are various ways in which people understand it now. These are some of the things I'll say are very recent, a few months to a year old. This is the proof of Sagas conjecture, then spontaneous stochasticity, so-called, which I will explain. And then I would also like to show you how most of the dissipation of energy is not uniformly spaced. It is happening in spurts. And what kind of spurts really enable you to have dissipation. And then I want to say a little bit about the so-called statistical conservation laws, which are supposed to tell us about the anomaly of scaling in turbulence. So these are all the types of problems people here as physicists think a lot about, but in a different context. So it should be relatively easy to follow what I will say. Well, that's what I would like to say. But let's start with something simple like this to keep our ideas in check. The kind of situation I have in mind is a box. When it is numerical, it could be a periodic box, but when it is experimental, just imagine it's just a regular box. And it contains in it a fluid which is of constant density, like water or air or something like that. And then it has a certain viscosity nu. And nu is just a symbol. Then I want to shake the box relatively gently, relatively slowly, and I keep doing like that. I can either keep doing like that, or I can just shake it first and leave it on the table. As I said, if you leave it on the table without continually shaking, because the energy decays, it will eventually die down. But if you want to maintain it, you just have to keep shaking it constantly. Now, if you do that, let's say the box is a size L, and let's say the velocity with which I probably should know where I am. Yeah, I should check the box at some velocity L, some velocity v. And now I want to know what the motion of the fluid will be. And it is governed by the Navier-Stokes equations, which I will not write down for you here. Everybody knows that, and if you don't know, it doesn't matter. So it's just equations of motion that govern the fluid. And if I solve the equations, subject to all the boundary conditions and so on, I should be able to say what the fluid motion will be. It turns out that the thing that determines for us is this combination of parameters called the Reynolds number would be very large. Velocity times the length scale divided by viscosity. So sometimes what I use in my talk is I sort of say low viscosity instead of high Reynolds number. You should sort of think they are similar in this context. And I'm interested in a case where the viscosity is low or the combination of these numbers, these quantities is very large. Now, what I know is that from measurement, in this case, this is a real a trace. If I take a line cut along the box, the velocity fluctuates like the one trace that is shown there, and the fluctuations are much, much smaller. They go to much, much smaller than the scale at which I actually shake the box. I may shake the box slowly, and therefore my input, my forcing, is at the scale of the box, but for whatever reason, the dynamics is such that I develop smaller scales and smaller scales and smaller scales and so on. And that's what you see. And that's what you would like to understand. And the number of degrees of freedom, as it is called, which is the smallest scale to the largest scale in the flow, would depend upon the Reynolds number. And in the laboratory, the Reynolds number could be 1,000 to about 1,000,000 or something like that. In geophysical or astrophysical flows, it may be 1,000,000 to 10 to the power 12. For example, in convection in the sun, the Reynolds number would be 10 to the power 12. And in those cases, the number of degrees of freedom, that is the ratio of the largest scale to the smallest scale, would be something like this. Landau gave a formula which says it goes like Reynolds to the 9/4. If you believe me, it's Reynolds number to the power 3. But you can see that if the Reynolds numbers are very large, these numbers of degrees of freedom will be very large, would be not exactly the number of molecules in this room, but it is very large. So the problem is therefore statistical in nature, but also because the equations, there are the deterministic equations that govern the phenomena. It's also a problem in PDEs and things of that sort. So there's a whole lot of things that come together in understanding turbulence. And of course, it's a practically interesting problem. So that's why engineering, physics, and math come together in this issue. So the first thing I want to say is that if I measure, let's say, at some point in space here, the rate at which energy is being drained out, so you shake the box, you input some energy, it's being constantly drained out just to keep it statistically stationary. And you measure this dissipation of energy here, or you average it over the box, whatever you do, that quantity has the property that it is independent of the viscosity of the fluid. Now that may look strange to you because energy dissipation usually is thought to be an effect of friction in the flow, which is the viscosity effect. Therefore, the more the viscosity, the more it dissipates, is what one might think. And in fact, you can make this a little bit more precise by actually looking at the equations. From there, you can find that the energy dissipation rate is like that. It's viscosity times the square of the gradients in the flow. So you have smaller scales and smaller scales. or you have larger and larger viscosity, you would think that the dissipation would go up. But this is not true. It's not true. And Taylor, 1935, that was very long ago, none of us were born at the time, said that the energy dissipation rate, I have to see what I'm doing here. Energy dissipation rate actually does not depend on viscosity, but it depends upon L, that is the scale at which you have stirred the flow, divided by the cube of the velocity with which you stir the thing. So that's what he said. And that's G.I. Taylor. And in fact, I took his direct quote from the paper. You can see that's exactly what he says. But the amazing thing is, if you read the paper, this one sentence has no connection to anything before that and no connection to the sentence that follows. So it's a kind of inspirational statement somehow. And for a long time, this statement had no real evidence, experimental evidence, although everybody knew that it's an anomaly. It's an anomaly because even when viscosity tends to zero, that is the symmetry breaking parameter, symmetry being energy conservation with time, the symmetry is not restored, and that's why it's called dissipative anomaly. And so what it says is that if I take d, this quantity here, take the limit of that as the viscosity goes to zero, it does not vanish, but it remains a quantity of odd unity. So that's the thing. We called it the zeroth law of turbulence at some point. And the whole question is how to understand this. So first let me show you what the evidence is. With some humility I say that until I created this graph, this grid turbulence in 1984, that is 50 years after the Taylor's thing, people had always thought this is true. Kolmogorov assumed that this is true. Many others assumed that this is true. But the experimental evidence came here. And what you can see is that if I plot this d as a function of Reynolds number, which is some other Reynolds number, but never mind. Increasing Reynolds number here means decreasing viscosity. So this quantity sort of changes from slow decline and then it remains constant at some value of odd unity. And that's what Taylor was actually saying. And I also could work out the low Reynolds number limit of this. And after this, many others have actually shown that this is in fact true. So that was nice. Then I also collected some computational data later on, 10 years later or 14 years later, and then that showed the same behavior. And now, of course, the most conclusive thing was by Kaneda in 2003, and thereafter there are others who have gone to very high values. If you can shine your laser on et al. And see, you will see my name as well. So that's the whole story of the dissipation being independent of viscosity. And the flow in which I collected all this stuff was, this is a flow in a wind tunnel, and this place here is a grid like this, grid of bars. Until the flow hits the grid of bars, it's very smooth, as you can see. Thereafter, it produces little wakes, and they mix up, and this is the kind of region where one is making all the measurements. So there are many caveats to what I am saying, but it is clear that the energy dissipation rate does not depend on fluid viscosity when the viscosity is small, or equivalently, if you produce a turbulent flow of some sort, whether you use air, water, or mercury, it dissipates the same amount. I mean, this is totally a counterintuitive statement. And so one ought to understand where it comes from, and that's what I'll try to explain. The hand-waving argument is usually that Well, the flow develops small gradients, and these gradients, which technically might be called boundary layers, become thinner and thinner as the viscosity goes down. So the product viscosity times the square of the gradient remains constant. But it doesn't explain anything to you. It simply is a kind of wishful thinking. And I've just said that there. And so, what is the better explanation? In fact, a more daring statement of what I just said is that viscosity is not at all needed for dissipation. You always think, everybody is trained to think that in fluid dynamics, the dissipation occurs because of viscosity. But the bold statement that Ansager made was that you don't need viscosity at all. And how does it dissipate if it doesn't have viscosity? And that's what I will say, what we know about it. It's an Eulerian point of view. Alternatively, or in fact slightly different point of view, would be of the same thing. It is so-called spontaneous stochasticity. I will try to explain what this is in reference to mixing. So those are the first two things on my slate. What is Ansager's conjecture? It's 1949. Ansager wrote this abstract in a little bit earlier, a very nice abstract, but he never published the results until a few years later in this obscure journal. I don't know how many of you know what you meant of. Anyway, he said, if you take Euler equations, these are equations without any viscosity, then Navier-Stokes equations, and squash the viscous term, that's the Euler equation. It has no viscosity whatever, and therefore normally one would have thought it cannot dissipate. He said, well, there are certain solutions of Euler equations that dissipate energy. And what are those certain types? These are the so-called weak solutions. Weak solutions are solutions that don't satisfy the equations at every point, but they are smoothed by a weighting function. So that's roughly how you might think of it. And not any weak solution will do, but weak solutions which are rough, that is of this type. I need a bar here. So this velocity difference between 2 points in space is not proportional to the difference, as would be the case if it were just continuous, but it is Holder continuous, so with this exponent h, and as long as this h is less than a third or equal to a third, you have dissipation. So how does it happen? If you have just a rough velocity, you would have dissipation without any viscosity. We will discuss that a little bit. And but that's one part. That is to say, Euler equations can be dissipative, but one has to still connect those dissipative solutions to the actual solutions of the Navier-Stokes equations. So turbulent solutions, Navier-Stokes equations with infinitesimal viscosity converge to dissipative weak Euler solutions. So there are two parts to the conjecture that Ansager made. Sometimes only parts of it are referred to as Ansager's conjecture. So let's see what the status of that is. I will not prove all this stuff for you simply because it takes us too far away, and also I don't know that I can do all that very well. So Ansager himself proved that weak Euler solutions are energy conserving if h is greater than 1/3. He didn't publish it anywhere, but Greg and I looked at it in the archives, and you can actually see that he has the proof. And later on, several others made proofs of this, going from Hilbert space to Wessow space and things of that sort. So that part is Ansager himself proved, you might say. But he believed that the critical thing was 1/3. The Holder exponent was 1/3, because that's what Kolmogorov thought for all the time, and I will describe all that later on. And that part wasn't proved at all for quite some time, but it has just come into being only now, I would say. These authors, a few years ago, they were close, but not 1/3. But now, Phil, I said, he actually showed that it is 1/3. And among the people who have been working in it are people like Tristan Buckmaster, who is in Courant. So the first part of the Onsager conjecture, that is the Holder exponent is less than or equal to 1/3, Euler equations have weak solutions that are dissipative, has been proved. But what has not been yet proved is whether those weak solutions are really turbulent solutions of Navier-Stokes equations. And that is the work still going on, and we are getting closer and closer every day. So that's the status of Onsager's thing. But let me go back here. Okay, I think everything got messed up somehow. I'm sorry. Now this is Euler's thing. This stuff I told about Onsager's thing is Eulerian point of view. But let's take a Lagrangian point of view, which may be more intuitively obvious, and that is the viscosity is not needed for dissipation, which is goes by the name spontaneous stochasticity. And it's better illustrated by a process of mixing, although exactly the same arguments will hold for the dissipation as well. So the mixing is something like this. Suppose I have a source of a plume of smoke or something like that. It diffuses outwards, and the diffusion is a molecular phenomena in general. But the point of turbulent mixing is that whether this is a smoke or a bunch of droplets or anything else you can think of, just some pollutant particles, they all mix at about the same rate. Now that's again the same counterintuitive thing, and that's what I will try to explain through this phenomena called stochastic spontaneous stochasticity. So in order to understand the problem of mixing, you have to solve this equation that I have written down on the top, which is the so-called scalar equation. This is like the Fokker-Planck equation for the concentration of the dye or the smoke or something like that. If you solve this velocity that is advecting this motion with this molecular diffusivity, if you solve it with respect to initial and boundary conditions, you have the problem. But an alternative way of solving the problem is to the Lagrangian, is by looking at the trajectories in the Lagrangian frame of reference. That is, a trajectory, if I take a particle, a fluid particle, and then you trace how it actually evolves in time, that's the Lagrangian trajectory. And its equation is simply this, dx dx, that is the increment in the spatial traverse, is simply an advection effect. That is, if you multiply the velocity by the little time interval, it tells you how much you have gone, except that you have diffusivity here, and this diffusivity is introduced through this through the white noise term I have written down there. This is a very standard process. This is like the stochastic differential equation for the Fokker-Planck equation on top. So with an initial condition like that. So if I have, therefore, really the solution of the transport problem, which is the one on top, is the same as if I had a particle and if it somehow went over the trajectory, and I have many particles, and these particles are all going all over the place, and if I know them all, I can tell you how exactly the problem has happened. Now, generally, the reason for introducing this noise here is basically that this particle position, you might imagine, is known only to within the Brownian motion of the particle, And of course, if the velocity is smooth, these trajectories are all following each other, and then you will have, or neighboring each other, and you have this sphere just gets deformed into another sphere, and the average of these various spheres will give you the average trajectory for the flow. If the problem were chaotic, if the motion that was creating the motion of these particles, the fluid motion that was creating the particle motion, was chaotic, you know that these particles diverge, but they diverge exponentially. And if the particle distance initially is very small, it will explode, it will go, the gap will increase, but it will increase exponentially. I'll make a little comment in a bit on that too. But if you have turbulent motion, that is, you have two trajectories like this, which are initially separated by infinitesimal amount. In fact, the infinitesimal could be exactly zero. The particles will just diverge explosively. And why does it do that? And it is the so-called Richardson Law of diffusion. And it says that if I have this distance here, initially whatever that is, and after a little while, t minus t naught, let's say, if they have separated that much, that separation distance, the variance of that, goes like t minus t naught to the power 3. So it explodes somehow algebraically. And notice that this does not have this formula, if you take it literally, does not have the initial separation at all. So whatever the initial separation, it will always explode the same way. Or I have just given here, take it literally. Not present in the formula is R naught. That means two particles that start exactly at the same point in space, after a little while, could have exploded by a distance which is given by that formula. You might ask whether this kind of, what this means is, if you have two particles at the same point and they evolve according to different trajectories a little bit later, that means you have lost the determinism or the uniqueness of solution of the problem. And how you reconcile it with the usual notion that the ODEs have a unique solution for at least for a certain point of certain time interval, is very easy to explain. All the uniqueness and existence theorems relate to velocity that is smooth, but the velocity here is rough, as I have already pointed out. That is this Holder continuity. So, in fact, this is not in violation of anything that we actually know already. And as I already pointed out, there is a contrast to be made between this kind of explosive separation and the trajectory separation in chaos, where R goes exponentially, these Lyapunov exponents, R naught being the initial separation. So if you squeeze R naught to 0, it will take infinite amount of time for the trajectories to separate, but that's not the case with turbulence. So if you think of it like that, then what it means is the rate at which they explode or separate from each other is independent of the viscosity or the diffusivity of the flow. And therefore, the mixing rate or how the trajectory spread are independent of the diffusivity. And that's why this anomaly of spreading that is independent of diffusivity takes place. So I have here a little extra slide to explain, but I think I might skip this. But basically it explains a little bit about how you have to be careful in taking limits of the, you want to consider a case where the Reynolds number is very large. That means the molecular diffusivity of momentum or vorticity also is 0. So is the diffusivity of the substance. So you have to know how to take the limit properly, which one goes first and which one goes later. And I have tried to explain here, but I would skip that in view of time. So that's about the first part of my talk. But actually, Mean is just nothing. Mean is just nothing for in a turbulent flow. Well, it's not exactly nothing, but it is a very small part of the information. If I look at the energy dissipation, I take a line, I cut along the box, and I measure the energy dissipation rate. It actually looks like this. So it is taking place in spurts, and almost nothing seems to happen, and then another little spurt, almost nothing, and so on and so forth. Sometimes huge values of the order of few hundred times the mean value take place, etc. For a trace like this, or a quantity like this, if I just give you the mean value, however important the mean is in terms of engineering applications, it doesn't tell you very much. If a mean is somewhere here, it's in the units of mean, so mean would be just buried in the thickness of the line I have drawn there. So it basically doesn't tell you anything at all. You want to know how to characterize this whole entity, and in fact, this is for some fixed Reynolds number. If you go to much higher Reynolds number or much lower viscosity, these peaks will just keep growing in terms of the mean value. Many tens of thousands of mean values are entirely possible for the experience we already have. And therefore, and they become very sporadic. They are very rare, but they do occur. Now, for such quantities, which seem to be almost zero good part of the time, suddenly go to very large values, and then become small again and go to large values. It's very hard to handle such things. So what one does is to average it locally a little bit. So you sort of smooth out a little bit, take a little sphere around the particle, and you ask, well, that quantity that you average may be a little better behaved than this very crazy signal that I've just shown here. So that's what it is. So you take epsilon. I'm doing this for a line, but you can do this for a sphere. You will call this epsilon r. This is epsilon averaged over r, and I have tried to show it here. So you just take that distance r, and you average over that amount. Now you write this epsilon r as r to the power alpha minus 1. Alpha depends on x, and I will tell you exactly what alpha is. So why do I want to write like this? If I write like this, just imagine whenever alpha is less than 1, when r goes to 0, it will blow up clearly. Smaller the value of alpha, the faster it will blow up. If alpha is greater than 1, well, when r goes to 0, it is smooth. Its behavior is very smooth. So in fact, I have schematically tried to show it here. If alpha, whenever alpha is very small compared to unity, you have huge spikes, or it represents huge spikes. Smaller than 1, but not so too small. Smaller peaks, and alpha equal to 1, it is just independent of space, and alpha greater than 1, it is very smooth. So now what I want to do is therefore I can imagine alpha being very small in here and here, for instance, alpha being still small but not that small in these regions, alpha 1 somewhere, and alpha greater than 1 where well, nothing seems to be happening, but they are small values and they are very smooth, in fact. So the whole idea is now, in this signal, collect those regions which have same value of alpha, or really alpha between some neighboring values. So maybe this one and this one are similar values of alpha, or same values of alpha, and maybe if you took a long signal, there are many such things. And now that's an isoalpha set corresponding to some particular value of alpha, and you ask yourself, what is the dimension of that set? How prevalent is that, roughly speaking? So I call that f of alpha. This is all the work that comes from Chicago when David was still there, for instance. I mean the notation and so on. So f of alpha is the dimension of this iso-alpha set. This is the multifractality. And so you can measure this f of alpha as a function of alpha, and it will tell you a lot. It will tell you a lot, and I will at least try to extract one thing from it. So a few years after you go into the lab, this curve emerges, and this is alpha and f of alpha here, and that's the way it behaves. So if, for instance, I want to know what is the dimension of the set with a certain value of alpha corresponding to 0.5, then that 0.5 line I've drawn, and then I intersect it horizontally, and it gives me something like 0.4 or whatever. I can't see it from here, 0.115, let's say. So that's the dimension of that set. And if I choose another value of alpha according to this curve, it will tell me what the dimension of that set is. Now this has there is one critical point in this, which is shown by the star, which is the dimension of the set from which all the... Yeah, sorry.
I'm not quite getting the dimensionality.
Yeah, okay.
Can you elaborate a little bit? And also, did you say, is this data or a simulation?
No, this is all data. Nothing simulation so far. So what you have to imagine is that because the thing is not uniformly spread in space, and it is very sporadic and large values somewhere, small values somewhere, you have to imagine that it is being made up of many sets which are overlaying on each other. And some sets have very large values and some sets have very small values. So they're all overlaying on each other, and the whole job is to extract or extricate those sets of the volume where the magnitudes are, and roughly speaking, of different numbers.
For example, if you were just talking about the fraction of the total volume that was in a particular class, I don't understand. So this sounds sort of maybe over my head in terms of...
That's what it is. You might think that's the way it is, yeah.
So you're not talking about fractal dimensions?
I am talking about fractal dimensions, but when I reduce the box size to very small values, it is the fractal dimension. It's in the limit, it is the same thing. F is the dimension of the iso-alpha set. So alpha is now telling you the strength of the singularities, okay? And then if I collect all those iso-alpha signatures and call that an iso-alpha set, its dimension is F. So this number here, this point here, where F is equal to alpha by the theory corresponding to this, is the one that tells you where the mean value comes from, and it happens to be 0.87 by measurements, and this has some meaning. I will try to explain that a little bit. And what is the meaning? I remember that alpha less than 1 corresponds to singularities. The further away from unity it is, the more singular it is, if you want to think of it like that. Because it is not that far from unity, it means that this is nearly singular, but not really singular, or weak singularities, if I might say. And because F, that is the dimension of the set, is less than 1, but it is not too far away from 1, it means it is nearly space-filling. It is not entirely exactly space-filling, but nearly space-filling. So in fact, energy dissipation comes from, therefore, singularities that are weak, because alpha is not far from unity, and they're nearly space-filling because F is not far from unity. So when you want to think about the dissipation, they're not coming from very large spikes, which are very sparse, or nor are they coming from everywhere in space, but only some parts of the space. So this makes things very complicated, but you can actually get a handle on the dissipation rate from this kind of observation. I would be happy to pause and explain a bit. Yeah.
I'm also not smoke dissipation and the energy. So you were making an analogy and following the trajectory, but what maps to the energy dissipation sort of?
Okay, I did say that, but it probably went past everybody here very fast. No, it doesn't matter. Even people in the front, it may have gone very well past. I went in the following way. This is the sequence of my thought. I want to understand how the energy gets dissipated in a turbulent flow. The first quantity that I want to understand is the mean value, that is the average. It's a fluctuating quantity, so I want to understand the average value. And it is important in, for example, if you are measuring the friction in a pipe, you basically want to know what the average value is. So I went through all the things on Sagas conjecture, I went through the trajectories and all this stuff, and that was only to understand the mean value. But then I said, well, mean value, however important it is, really is not telling you all that much about the process, because it's such a hugely fluctuating phenomenon. I want to understand a little bit about the fluctuations themselves, and this is the way in which I try to understand the way the fluctuations take place. So what it means is that if you are looking at a combustion flow, for instance, the reaction rates are not uniformly spread. They are sporadic in space, and some places it's reacting very rapidly, and in some places it is not. Just in any turbulent phenomenon, things are not uniformly spread, but they are spread in this sporadic way. And the higher the Reynolds number, that is lower the viscosity, the more the difference between the huge top values and the low values. And how you understand that, this is all phenomenological at this level, unless I actually have a theory for this. Only some parts of it are amenable to theory. I think you can begin to understand it geometrically and things like that. So that's my pitch. So moving on, one more. I will skip this, and I will skip this as well. So the last item is related to the so-called Holder exponent. We call the velocity as rough, and I want to understand what this roughness is and what it has to do with any physical ideas we may have about conservation laws and things of that sort. So ignore this for now. So I take the velocity difference, which is what I have always been doing, and if you have this kind of expression where it is not simply proportional to r, but is proportional to r to the power h, where h is a number which varies at different points in space, and we already talked about the values of h less than or equal to 1/3, so there are other values as well. So I want to understand where all this comes from, and if I could say something about its implications. One of its implications is that if I take the moment of delta ur, this velocity difference, any order moment, say n, take the average over space or space generally, so that will now, the same thing will yield r to the power some zeta n, which are the scaling exponents. If you remember how you do Legendre transforms in either physics or in mechanics, you will very easily understand how you go from here to here. Basically what you do is, you have this quantity, you raise it to the power n. Now the equivalent of space averaging would be averaging over, integrating over h, all possible values of h, and then you eventually have this kind of relationship. Now this is the scaling relationship of the sort that people in critical phenomena know for a very long time, and basically what we know is, what we would like to know is how these zeta n's come about and what their source is. For example, I would like to know whether there are some conservation laws associated with it. Now, the only theory that one has is for this third moment, which simply says it is proportional to r. This is an old result due to Kolmogorov, and therefore this gives rise to the fact that the third moment is like r. The velocity difference characteristically would be like r to the power 1/3, which is what Ansager assumed and tried to prove, and which has been proven since, etc. So that is. So I tried to say the same thing here. So from this comes the notion that delta UR is simply r to the power 1/3. That is, you have a Holder continuity with an exponent 1/3. And so if this is the case, then all exponents can be computed if you know one of them. That is, you know 1/3. If delta UR is going like r to the power 1/3, nth moment will be n/3. And that is the relation. But if you measure them, and that takes a lot of time and has taken several years for several people, you find that that is not n/3, and it is a concave function. So, in fact, I have here a set of data from this paper I wrote with Gregory Falkovich. And what it says is the difference between the measured zeta n and n/3 is this as a function of n, and you can see that it is substantial. And the Kolmogorov result, or this one here, would have just given 0 along for all n. So it would be that number. So in fact, therefore, the problem really now is you have many exponents, none of which is related to another in any predictable way, in any way that I can see. In normal phenomena, in normal scaling phenomena, you would have thought that, well, if I know the third moment would scale like r, nth moment would scale like r to like n/3 from here. But in fact, what this is requiring you to know or understand is how each order moment behaves differently from all other orders, and so you have to have a theory for each of these exponents. And this is the big wheel in scaling phenomena in non-equilibrium problems in general. Turbulence just happens to be a paradigm of those phenomena. So what do we know about this? I would only take one more slide and then show you, and then I would finish my talk. So this result is actually a result on a statement on breakdown of time reversal symmetry. I'll tell you what I mean by that. If I take change t to minus t, then of course velocity changes its sign, and therefore this quantity will change sign, but this quantity does not change sign. It's just the separation distance between the 2 points. So in fact, if time reversal symmetry were to hold, this quantity would be exactly 0. But on the other hand, if you go through the Navier-Stokes equations, then you know that this is in fact a finite quantity, and therefore generally you know that a thing like time reversal symmetry does not work. What it means is, in a range of scales r, energy always has a habit of going in one direction and not going in both directions statistically on the same average value. If you had detailed balancing, for instance, what goes from big R to smaller r would be identical to what goes from smaller r to bigger R. But what this is saying is, in fact, that is not true. There is an energy cascade from in a certain direction, and that direction happens to be from large to small. So, therefore, if in fact it is true that there is a directional cascade of energy, and this just progresses in certain way until it is dissipated, then this energy is cascading at a constant rate. So the violation of time reversal symmetry here is the same in some sense as the conservation law corresponding to the flux of energy from large scale to small scale. So this relation here is then following from this conservation law relating to the constancy of flux. And this, therefore, the third order moment, this would be zeta 3, which would be unity, and that is coming from this breakdown of time reversal symmetry and the constancy of flux. The question is, in order to determine these other exponents, what kind of other conservation laws are there? What kind of broken symmetries are there in the problem? That would be an interesting question to answer. Just on this, it's a wishful thinking to some degree, as you will see, but it's a good question to ask because we know where this comes from. Therefore, we think there may be other conservation laws that may define other exponents. I've tried to say this in words here again. The Kolmogorov result, that is the one I had shown before, is a statement that there is the breakdown of time reversal symmetry. Time reversal symmetry would have made the third moment 0. Equivalently, this is a statement on the conservation of energy flux from one scale to another. That is, the third order exponent is determined by the conservation of energy flux. Are there other conservation laws that determine the exponents of other orders? So far, none in the traditional sense. There are not that many conservation laws to go around. But there seem to be so-called statistical conservation laws. So this is the new idea. I hope it has some general validity, but we don't know whether it is generally valid or not. In physics, you, at least as I see it, you have some idea that works in one context. You think it may be valid in other contexts and try to verify whether it's true or not. And so this is the hope, and I want to say what we know about it now, or what we think we know. So the statistical conservation laws are sort of like this. They are not valid, or they are not conserved at every instant of time, but over time, averaging, they are in fact conserved. So this is, I took this statement from this paper by Falkovich and others. And what has been shown is as true is for the so-called Kreiknen model for a passive scalar. This is a model whose details we do not need to worry about here. So it's the equation for the scalar advection that I had written down earlier. Instead of that full equation, full PDE, you write down a model for that, and Kreiknen did that in 1968. And for that model, it has been possible to show or construct statistically conserved quantities which give you other exponents. And what are those statistically conserved things? They are the products of fluctuations of shape and the geometric expansion of groups of particles. Let me explain what that is. So at t equals t naught, let's say I take 3 particles which form, let's say, the vertices of this triangle. And again, another set of 3 particles which form the vertices. And at small times, there are all kinds of shapes of these particle triangles. Some of them like this, some of them stretched out in another direction. So the fluctuations in shape are huge. But as they evolve, what happens is that all of them evolve to roughly the same shape, that is, type of equilateral triangles, and they also enlarge because of the explosion that we talked about of particle trajectories. So if you construct a certain quantity that is proportional to the product of the fluctuations in shape and the size of these shapes, then such quantities can be conserved. So initially you have huge fluctuations in small shapes, and later on you have large shapes and small fluctuations. That is, they all tend to be of the same shape. So in general, therefore, you can construct a quantity that's product of the two, and that is conserved, and that kind of thing has been shown to be true for the for the Reiknan's model, and one imagines, therefore, that in fact it is valid for other types of things as well. And that's the reason why you have these multi-exponents, and for each of them you have to construct a certain theory that gives you what their origin is. But if you never really understand everything in detail, if you understand one thing very well, you sort of think that maybe something similar might be true. So that's roughly how the theory has been going on in the last few years. So I sort of summarize for you what I have tried to say. The average value of dissipation, which hundreds of years of training of fluid dynamicists have always said occurs because of viscosity, may occur without viscosity. I mean, that's for at least those who have lived in this domain know it could have a profound impact on one's understanding. And how does it come about? I try to explain what we know. Onsager's bold conjecture and this spontaneous stochasticity. And then I try to characterize these huge fluctuations in the dissipation rate. Not very successfully, if I understand the question that you asked. But anyhow, that's what I can tell you. And I also tried to say this so-called anomalous scaling, that is the scaling of these velocity differences which characterize the roughness of the flow, how the exponents that let you scale, how they are all different, and how the differences among them can all be attributed, presumably, to the multiplicity of statistical conservation laws. And I tried to sort of explain at least one that has been known to be the case. So that's what I now think about on my trip from here to Brooklyn. And so thank you very much for giving me the opportunity to say something here.
Questions?
Yeah. Should there be some relationship between your second point and your third point?
Yes.
This very small
Definitely.
exponent point.
Definitely, yes.
17.13.
Yeah.
And your last string about
Yes.
variance in conservation.
There is a relation, yeah. I just. It's provable. By provable, if you mean from the dynamical equations, no. There are intermediate steps which are provable.
Relating.
Proof is a very difficult concept. Nothing is known at the level of that passes a rigorous mathematician. But there are physics type proofs.
A related question. Supposing your second thing, instead of being 0.3 was 0, meaning everything was logarithmic. Is there a model which gives logarithms and solvable?
Say that again. Instead of
0.13, which you deduced from some experiment. Let's say it was 0 from the negative side. So
right. No, I understand. Yeah.
So logarithmic problems are quite often controlled.
Yeah.
Are there such models?
Yeah. If the exponents become small, you cannot distinguish between a logarithm and a power law in an actual plot. So your question to that degree is a very valid one. But the systematic theory within quotation marks, the framework, let's say, you build, is valid for small exponents as well as very large, relatively large ones, which cannot be approximated by logarithms. So it's not thought to be a logarithmic type thing. It's all power law. There is another reason for preferring power laws, and that is you think there are ranges of scales, intermediate range of scales, which are not influenced by how you stir the flow or how you take away the energy. So intermediate range of scales are really scale invariant in some way, and scale invariant things are power laws. So that's the...
Logs are also limited.
Well, logs, you will need something, right? Logarithm of R over L or something like that, when then L becomes an important thing. Now, it doesn't mean what I'm saying is right. It may very well be there are some simple ways in which these large scales can influence everything. And they do. Even in power laws, you can actually tell how they influence. But basically, power laws are preferred, I think in part because even before critical phenomena were known, there's a Kolmogorov thing, 1941, people knew power laws at that time. In fact, I would say the intellectual flow of ideas came from turbulence to critical phenomena, and then now, of course, is flowing back to turbulence. And that's what I would say.
One third in the Richardson Law, even the cubic law, does it have something to do with getting one third of it?
Yes, it does. It should, but I can't see enough of it to tell you that it must be the case. How it must be, but I could think about it and tell you. It must, yeah.
And then just one quick question. You said that no matter what the say triangular shape or shape, it ultimately goes to equilateral triangle.
Yeah.
Sort of symmetric.
Yeah.
What happens in 3 dimensions?
So you will have objects which are made of which are multiple. You can construct quadrilaterals or whatever it is, quadrangle. That's a 4-point thing. You can do in 3D. I mean, this is all 3D. So they are not going on plane. They are. If you take 3 points like that and define a triangle, they could do whatever they want to do, but it would be in 3D.
Symmetric is different position.
I'm not sure I know what you're asking.
Well, you take planar, the irregular shape of the world.
Yeah, I just wrote it on a piece of paper as a plane, but it doesn't have to be in plane at all.
Yeah. Why don't we continue across the street?
Okay, all right. Thank you.